So for these videos, I will explain about loading distributions. Okay, so let's start from the secondary beam. So what is secondary beam? Okay, so secondary beam will distribute the load acting on it to the primary or main beam via its supports reactions. Means the secondary beam is directly distribute the load to the main beam because it don't have the columns here to support it. So the load from the secondary beam will distribute to the primary beam, okay, or also called as main beam via the support reactions. Okay, so the load on the secondary beams here, it will distribute to the left and to the right support to the main beam here and here. Okay, so here is the assignment for you guys. Okay, so you can refer to the previous videos that I already have a calculation about how to calculate the load. But this one is, okay, loading distribution for the secondary beam. Okay, you need to determine the characteristic permanent and variable actions, okay, the GK and the QK, on beam B13. Okay, B13, you need to calculate on B13 as just now like this. But then, okay, this column B2 has been removed. Okay, so given the following data, okay, the unit weight of concrete is 25 kilonewton per meter cube. Finishes, ceiling and surfaces is 2.0 kilonewton per meter square. Variable action for all slab is 3.0 kilonewton per meter. So consider the column B2, 2B, okay, which is 2B here is not exceed, and then the beam 2BC 1200 times 450 mm is a secondary beam. Means now you need to calculate the secondary beam of the loading of secondary beam this and then distribute to this beam 1 to 3B. Okay, so here you will have a point load here. So what is the point load here? You need to calculate it for this assignment. Okay, so let we talk about the loading distribution for roof. So typical Malaysian buildings rooftop can be divided to three, which is the flat roof, hip roof, and also gable roof. So load transfer mechanism of flat roof is similar as slab loading distribution. So for hip and gable roof, okay, which is the pitch roof, the roof load will transfer to the beam via the roof truss system. Okay, so the roof truss system, this is an example for the roof truss system. Okay, we have the permanent load, permanent actions GK, okay, which is from the roof tile, metal deck, insulations, self weight, battens or pullings, ceilings, and also service. And what is the variable actions? The QK here, okay, is the 0.75 kilonewton per meter square to 1.25 kilonewton per meter square, which is for the maintenance purpose. Okay, so you can see that this is an example of the roof truss system. Okay, so the weight of roofing material can be referred to manufacturer catalog, depends on the architecture design. So type of the loading the roof truss system, actually we have two. One is cold form steel, another one is hot rolled steel truss system. So for this cold form steel truss system, okay, the span must be less than 13 meter. If more than 30 meter, you need to use the hot rolled steel. Okay, so for this steel is designed by fabricator, and then load can be distributed to the four side of roof beam by using simplified approach. Means each side is 0.5 times n times lx or 0.5 times n times ly. So it's distribute evenly to four edges. Okay, so for four edges evenly. Okay, easier and faster the calculation. This is the estimation for it. And hot rolled steel truss system here is for the span greater than 30 meter, and this is designed by engineer where the roof load can be distributed to the roof beam via the truss support reaction as at the respective site. So I believe this one, how to calculate the truss, you already learned in structural analysis, which is the previous subject before this subject. So I will skip this so you can refresh yourself with the truss calculations. Okay, so for the loading distribution for the axial load, okay, so the beam will distribute the load into columns. So the column is in the form of axial load. the load from the beam will be transformed in axial load, okay, via the summation of support reaction at particular beam column joint. So you can see that this is the beam, okay, this is the beam, this is the beam, okay, the blue color is all the beam. So the load from the beam will distribute to the column, okay. So axial column in column A, so for example this is column A. So the load here is R3 plus R1 plus R3 plus column self weight. So let we see the R1. What is R1? Okay, so for this R1 you can see that R1, R2 and R3. So this is 3 columns here, okay, so this is R3 here, so this is supposed to be this side. So here is R1, R2 and R3. Okay, so this is the load from the R3 for this side. And then here you can see that this is R1, R2, R3, R4. So here you have 3 span and 4 support. This one is at this side. So load from here and from here and from here will go to the column here, okay, this is the column A, and together with the self weight. So this is the axial loading in the column A, okay. So you can see that this is the figures that showing you how the load distribute from the slab to the beam, from the beam to the column, and from the column to the footing, okay. So structural analysis is the primary purpose of structural analysis to establish the distribution of internal forces and moments over the whole part of structure to identify the critical design condition at all sections. So in practice, there are many different loads act together, and this has to be considered in the structural design. So various combination of the characteristic loads such as GK, okay, QK, and WK, the wing load, okay, and their partial factor of safety must be considered for the loading of the structure. So we need to use the partial factor of safety to make sure the structure is safe for the design, okay. So the RC beam must be designed to resist the ultimate bending moments and shear force. In some cases, the beam is also required to resist torsional moments and also axial force. So the beam is required to achieve serviceability requirements such as deflections and cracking. So the loading arrangement, okay, so for the loading arrangement here, according to class 5.1.3 in MSEN 1992-1-1, okay, so you can refer to the Euro codes, okay. So in considering the combination of actions, the relevant case shall be considered to enable the critical design conditions to be established at all sections within the structural parts or parts of the structure considered. So for simply supported beam, the analysis for bending and shear force can be carried out using statically determinate approach. For the ultimate limit state, the ULS, we need only consider the maximum load, which is 1.3 GK and 1.5 QK. So this value are from the Eurocode. You can read it through the MSEN 1992-1-1, the class 5.1.3, and then you can refer it how they get it, okay. So you can see that, so this beam is W equal to 1.35 GK, which you calculated from the assumption, and 1.5 QK. And if you have any secondary beam, so you will have a point load. This is from the secondary beam, okay. So for continuous beam, okay, the following simplified or load arrangement based on the national annex are recommended. So we have 2 load sets, which is set 1 and also set 2. So for set 1 is alternate or adjacent space loaded, and number 2 is all or alternate span loaded. So for the load set 1 alternate or adjacent space loaded, okay, for the continuous basis, alternate span carry in the design permanent and variable actions, variable loads 1.35 GK plus 1.5 QK, and other span will carry out only the design permanent load, okay. And another one is another 2 adjacent space carrying the design permanent and variable loads 1.35 GK plus 1.5 QK, and all other spans carry only the design permanent load, okay. So this is the imagine the image for it, how you do it. Okay, so for alternate span loaded, okay, you can see that this, when this span we loaded with the maximum load, and this one we only put the design, we only have the design permanent load, so it's alternatively put the maximum and the design load. So this is 1.35 GK plus 1.5 QK, and this is 1.35 GK. Okay, so another one, and then this one you have two cases, which is this is case 1 and this is case 2. So for case 2, you start from the 1.35 GK, and then 1.35 GK plus 1.5 QK, and then again 1.35 KK, which is only the design permanent loads, and this is the design permanent and variable load. So for the adjacent span loaded, okay, is like this. You need to have these two adjacent space loaded with the design permanent and variable actions, and then another span you only loaded with the design permanent loads. So this one start with this span, these two span, and then this case 2 you start with the second span and the third span, and then third case here you see this is the last two span loaded with the design permanent and variable load. So the load set 2 all or alternate span loaded for the continuous speed is first all span carrying the design permanent and variable actions. So all the span carry the same variable and same permanent and variables load for the design. Another is alternate span carrying the design permanent and variable actions. Okay, so one is carrying the 1.35 GK and 1.5 QK, and other span carry only the design load. So you can see that for this span carry the permanent and variable load. This is only permanent plus VK plus GK plus QK. This is only GK, and this one is GK only, and this is GK plus QK, GK plus QK. Okay, so this is load set number 2. So the difference with the previous one is this. Okay, so the shear force and bending moment diagram can be drawn for each of the load case required in the patterns of loading. You need to draw this. A composite diagram comprising a profile indicate the maximum value including all possible load case can be drawn. You need to draw it and combine all the shear force and bending moment diagram in one diagram, and it is called as envelope. So in this subject, the load set 2 will be further considered in the structural design. So we will use the load set number 2. Okay, all span carrying the permanent and design load, which is all span will carry 1.35 GK plus 1.5 QK, and alternate span, okay, which is one carry the 1.35 GK 1.5 QK, another span carry the 1.35 GK only. Okay, so you can see that this is the example for the envelope load case later. Okay, so this is from the case 1, which is full, all the span loaded with the maximum GK plus QK. Load case 2 is, okay, you set the alternate span loaded with the 1.5 GK and 1.5 QK. Okay, this is the case number 3. Okay, so you need to draw this SFD, and this is bending moment diagram. So you draw all these three, you combine into this, and you draw these three, you combine into this. So this is the envelope for the shear force diagram, and this is the envelope for bending moment diagram. Okay, so method of structural analysis. So there are 3 structural analysis methods may be used in order to obtain the shear force and also bending moment for design purpose. So they are first elastic analysis using the moment distribution method, which is we choose the modified stiffness method, which is faster and easier to calculate. Okay, and this one you already learned in the previous subject, which is the structural analysis. So you can refresh yourself with it also. And later I will show you an example on how to calculate this using this method. And number 2 is simplified method using the shear and fork moment coefficients from table 3 in BS 8110 part 1. It gives you a standard data for you to calculate it. And number 3 is using the commercial analysis software such as StepPro, Steam, Orion, Tekra, and so on. So by using the software, you can key in the value and the span and so on, then you will come up with the envelope. Okay, so for first, the moment distribution method is only involving distribution moments to join repetitively. So the accuracy of moment distribution methods is dependent to the number repeat, which does and usually more than 5 repeats real enough. You repeat 5 times, then enough. Okay, so right value will be acquired when no more moments that need distributed. So in general, the value is dependent to several factors such as fixed end moment, carryover factor, moment, and member stiffness factor, which is the distribution K value. Okay, so we go to the next slide. So moment distribution methods for the fixed end moments, okay, the moments at fixed joint of a loaded members are called as fixed end moment, and this moment can be determined from the table below depending upon the type of loading on the member. So if you have a point load, then your fixed end moment will be this value using this formula, and this is for UVL, this is for UDL, this is for UVL, and also this is moment applied on span, UDL on the right, UVL maximum at the left, and UDL on full span. So you can calculate. Normally we will use quite a lot for the UDL and also point load, but also depends on the case you need to do. Okay, so for the CARE and also COF, so far end member pin and roller support is K equal to 3 EI over L. Okay, and then for this, you can see that this is an example. So this is a far end member pin or roller support. So here is 3 EI over L1, this is 4 EI over L2, this is 4 EI over L3. So if the internal member and far end member fixed at end support is 4 EI over L. So this is internal member, so this is 4 this KBC is internal member. Okay, and this is far end member, this is pin support, so this is here, and this KCD is 4 EI over L3 because it's fixed at end support. Okay, so the carryover factor is to a fixed end is 0.5 always, and otherwise is 0. So if only fixed end, then you will give 0.5. Otherwise, if it's this roller or pin, is all 0. Okay, so distribution factor, okay, how you calculate the DF is equal to K over K total. So here you can see that far end pin support for DF is 1, means that if the A just now is the pin support, that is 1. Okay, and far end fixed, if it is fixed at here, that is 0, DF equal to 0. So here you will have this DFBA, okay, is equal to KAB over KAB plus BC. Okay, so here for the DFBC is KBC. Okay, here different, here is KAB and here is KBC. So when you calculate this side, this is equal to this, and when you use to calculate DF, you need to use the K for this value. Okay, so KBC over KAB plus KBC, and so on. So we have an example 3 here. I will explain to you later. Okay. Okay, so let me explain this example, which is example 3.3. So a series of 250 mm times 450 mm reinforced concrete beam spaced at 3 meter centers and spanning 7.5 meter support at 175 mm thickness reinforced concrete slab as shown in figure 2.1. So here you can see that A to B and C. Okay, here is 3 meter, here is 3 meter, and then this is the span B1, 2. Okay, so if the variable flow action is 3 kilonewton per meter square and the load induced by the weight of concrete is 25 kilonewton per meter cube, calculate the maximum shear force and bending moment of the beam 1, 2. So you need to calculate the shear force and bending moment for this beam. Okay, and then this is a precast slab, so the load will distribute, okay, in one way to here. The load will distribute from the slab from one way to here, okay, and to here. Okay, so this is the 175 mm thickness slab, okay, which is mentioned here, and this is the 400 mm beam depth. Okay, so how you calculate? First, we start with the loading from slab. So the permanent action, okay, GK is including the thickness times the unit weight of the concrete, which is the self weight. So this is the self weight of the slab. So it's 0.175, this is in meter, times 25 kilonewton per meter cube. Okay, so when you multiply it, you will get 4.38 kilonewton per meter square. And variable load QK is 3 kilonewton per meter square, and this is provided in the questions. So total ultimate load is 1.35 GK plus 1.5 QK. Okay, so this is from the Eurocode, okay, you can refer to, and this is the maximum when we calculate for the simply supported beam. So 1.35 times 4.38 plus 1.5 times 3, so you get 10.41 kilonewton per meter square. So this is for the slab. And for the beam, okay, so from the beam you have ultimate load from the slab. So how can we calculate it? We will get the total ultimate load for the slab per meter square times, okay, times the length, okay, which is from the AB 1.5 and ABC 1.5. Why? Because here the distance here, okay, is distribute 1.5, means the load from this part will distribute half to here and half to here. That's why we times the distance 1.5 from AB and 1.5 from BC. So you multiply it, you get 31.23 kilonewton per meter. Okay, and then for beam self weight, GK is 25 kilonewton per meter 3, which is the unit weight of concrete. And also then we need to times 0.4 times 0.25. okay, so this is the 2, then when you time this, you will get 2.5 kilonewton per meter. Okay, and then you ultimate load for beam is 1.35 times 2.5, okay, then it's 3.35 kilonewton per meter. Okay, so total ultimate load W here is 31.23 plus 3.38, so you get 34.61 kilonewton per meter. Okay, so after you get this value, total ultimate load here, you get a W, okay, from the calculations, ultimate load. Then you need to get the maximum shear force. So we know that you can see that if you normally from the calculation from the mechanics of materials that the subject you learned before this, you calculate when there is a uniform distributed load here, then you can calculate the support reactions, and then you can determine the shear force, bending moment diagram, shear force diagram and bending moment diagram. So the maximum shear force at here is the maximum shear force. So for this, you can calculate from the equations WL over 2, because it's only one load here. Okay, so when you calculate this, you extract, you get 129.79 kilonewton. And also the maximum load, maximum bending moment, it will be occurred at the middle. Okay, so the formula for this is WL squared over 8. So these two you need to memorize it. Okay, so can speed up the calculations. So 34.61 W times 7.5 power of 2 over 8. So you get the answer is this. Okay, so settle for these questions. So you get the maximum shear force and bending moment for the design for the next step. Okay, so let's we go to the example 3.4. Okay, so for example 3.4, figure below show the first floor layout plan of commercial buildings of all beam size are 300 times 500 millimeter. Determine the followings. Okay, so first you need to calculate the characteristic permanent and variable actions at on the beam 1AE. So later I will show you the figure. If all slab thickness are 150 and the brick wall height is 3 meter. Okay, and shear force and bending moment envelope of beam A1AE. Okay, and then the provided data is as below. So variable load on slab is 4 kilonewton per meter square. Finishes, ceiling and services is 1.5 kilonewton per meter square. Unit weight of concrete is 25 kilonewton per meter cube. And brickwork is 2.6 kilonewton per meter square. Okay, so this is the layout for that. So you can see that we will calculate the beam 1AE, okay, which is the GK and QK. So here you can see that this is the beam from 1A to E. So this is a continuous beam with 1 span, 2 span, 3 span, 4 span. 1, 2, 3, 4, 5 and 5 support. And you have the average, the even span size, which is 8 meter. Okay. So the solution is, first, we always calculate the action start from the slab. So characteristic permanent and variable action on the beam AE, okay, action from the slab. So permanent action GK is self weight of slab plus finishes and ceilings and services. So self weight is 0.15 meter, which is the thickness, okay, times the unit weight of concrete. Then you will get 3.75 kilonewton per meter square. Okay, and then the finishes, ceilings and service, you will get 1.5 kilonewton per meter square. This is provided. And total permanent actions GK on slab is equal to 3.75 plus 1.5, so you get 5.25 for the permanent actions. And variable load on slab is 4.0 kilonewton per meter square, and this is provided in the questions. Okay, so load case 3, okay, so we calculate, and it is similar to load case 2. So you calculate, okay, so 24.72, 33.72, 24.72, 33.72, and then you calculate same with this method. So we get 131.84, 179.84, 131.84, 179.84, and then this is similar with this. Okay. And then we need to start calculate with the moment distribution method. So you need to draw this table, and then you put a part AB, BA, BC, CD, CB, CD, DC, DE, and ED. Okay, and then the distribution factor you calculate just now, you need to put input into it. So 1, 0.43, 0.57, 0.5, 0.5, 0.57, 0.43, and 1. Okay, so the fixed end for COF is 0.5 and otherwise is 0. So this modified moment distribution method. Okay, so this one we're using the moment distribution, modified moment distribution method. So you calculate the FEM here, which is the one, just now you calculate the value. Okay, so it's negative 179.84, 179.84, negative 179.84, 179.84, negative 179.84, 179.84, negative 179.84, and this is 179.84. So you solve it. Okay, so you have to solve this using the moment distribution methods, and then you will get the M moment, okay, which is 0, 231.09, negative 231.09, 154.215, 754.215, 231.09, negative 231.09, and 0. Okay, so this I will not explain long because this one is supposedly you learned in the previous subject, and then you can refresh it yourself. Okay, so also for load case 1, load case 2, load case 3, you need to repeat the same thing. So you need to do this moment distribution method, the modified moment distribution method, and then you get the final M moment. Okay, so after that, okay, you can see that you will get the value for the final M moment. So you draw the beam again with the W here. Okay, this W is from the, this is for the load case 1. You can see this is the load case 1. So load case 1 here is 33.372 for each span. And then you insert the M moment, which is you calculated here. So this is the M moment for each internal support. Okay, so after that you calculate, after you do this, what you have to do now, you need to calculate the reactions, okay, the RA, RB, RC, RB, RD each. reaction for each support. Okay, so you calculate this. Okay, so you break it to each span. So for span AB, you calculate this. So the total, you can start with total MA and total BB is the same thing. So it depends on your personal preference. So total MB is equal to 0. So this is clockwise. So 231.09 minus 33.72 times 8 over 2 plus RA is equal to 0. This is counterclockwise, this is clockwise, this is clockwise, okay, positive, and this is counterclockwise, that's why it's negative. So you calculate this, you get RA equal to 105.99 kilonewton, and also then total Fy is equal to 0. Okay, so RA and RB minus 33.72 times 8 is equal to 0, so you get RB is 164.25. so you input the value into here, you get 105.99, and this one you input into here is 164.25. okay, so you need to repeat this for this pen, and also this pen. Okay, so I show you the example here. So for span BC, you need to calculate and you get the RC and you get the RP. Same thing, you start with calculate the total moment equal to 0, then you get the reaction force for one side, and then you calculate another reaction support. Span BC all the same. Okay, you get the RD and RC, and then span DE also you get the RE and RD. So once you get all the reaction force, then you include into this. Okay, so you can draw the shear force. You can draw the, oh sorry, this is shear force diagram and this is bending moment diagram. So you draw this shear force and bending moment diagram, you will get one envelope for the load case 1. So you need to repeat the same thing for load case number 2 and load case number 3. Okay, so due to the time constraint, I will not able to show you on each cases, but you can practice yourself. Okay, so you can see that when you combine it, and this is what we call the load envelope. So this is a shear force envelope for this combined with case 1, case 2 and case 3, and this is bending moment envelope for both 3 cases. Okay, so this example is until here. So thank you for watching. Okay, so another one is the simplified method. So the analysis using moment distributor is time consuming, is taking a lot of time, and it is more conveniently carried out using the standard computer technique. Okay, so if you have too many cases, it is better for you to use the Step Pro or other software helps in order to get a faster calculations. Okay, so therefore as a simplification of BS at 110 clause 3.4.3 can be used. So table 3.5 are given here, which is the example here, and here this table. Okay, this table 3.5 given in BS 8110, which is enable a conservative estimate of shear force and bending moment values to be determined for the design of continuous beam. So there are conditions must be satisfied in each case before this table can be used, and there are 4 here as listed. Okay, so the beam should be approximately equal span. Okay, it cannot have a one very long span, another one very short span. Okay, and characteristic variable action QK may not exceed the characteristic permanent action GK. Means the permanent action must be greater than QK, else you cannot use this simplified method. And load should be substantially uniformly distributed over the 3 or more span. And variation and span length should not be exceed 15% of the longest length. Your span length must be within the 15% difference. Okay, so we can see this table. Okay, so from this table you can see that at outer support for moment you will get 0. For shear you will get 0.45 F. Okay, and F is the total design ultimate load, which is the 1.51335 GK plus 1.5 QK, and L is the effective span. Okay, at near middle of end span you will get 0.09 FL, and this is none. Okay, at first interior support you will get this value, which is negative 0.11 F times L, and this is 0.6 F. At middle of interior span you will get 0.07 FL, and this is none, no value. And interior support, at interior support, which is in the interior support, okay, the each for each support the moment is 0.08, negative 0.08 FL, and the shear is 0.55 F. Okay, so this is the example for the simplified method. You can see this is 0.09 FL, which is near the middle of end span. Okay, this is the end span, this is middle of end span, near it. And then this is at the first interior support, so this is the end, and then it's 0. Okay, so the first interior support, it will be 0.11 FL, negative, yeah. Okay, and then at the interior support, you can see that for the interior support is 0.08 FL, which is negative also. Okay, and also at middle of interior span is 0.07 FL. Okay, so if you have more, and this is at the internal, then is 0.08. Okay, so this one is at the left, and let's say your simplified method support here is at the right, then you can reverse this figure, you will get the below. And for shearing stress, okay, at the outer support is 0.45 F. And then at the middle is 0. Here is 0. Okay, and then at the first interior support, the 0.6 FL is here. Okay, for the first interior support. And at the middle of interior span is 0. And at interior support is 0.55, 0.55 F. So this one straight away you can calculate and get the value. Okay, so for the example from the previous example, okay, you can see this. Okay, GK is 18.35 and QK is 6. Okay, and then you can see that each span is same, and also GK is higher than QK, so you can calculate using this. F equal to 1.35 GK plus QK, so 1.35 times 18.31 plus 1.5 times 6 is equal to 33.72 times 8 meter. Okay, so totally you will get 269.75 kilonewton. Okay, so this is the load. So when you calculate the 0.45, okay, just now the one you calculate is already FL, so you calculate 0.45 F, you will get the value for first one, and then you calculate, you will get all this value. Okay, so you can practice, and then how you calculate it, double check. Okay, so this is for the shear force diagram, and this is the bending moment diagram. Okay, so this is faster way, is it? You don't need to go through the moment distribution method, which is quite long. You need to calculate one by one, but this is simplified method, but you need to follow the rules, then you can use it. There are terms and conditions for it. Okay, so for moment redistribution, so what is moment redistributions? Okay, so plastic behavior of RC at the ultimate limit state ULS affect the distribution of moment in structure. So to allow this, the moment derived from an elastic analysis may be redistribute based on the assumption that plastic hinge has formed at the section with largest moment. So from the design of point of view, some elastic moment as support can be reduced. So, but this will increase others to maintain the static equilibrium of the structure. So the purpose of moment redistributions is to reduce the bending moments at congested zone, especially at the beam column connections of continuous beam support. So therefore, the amount of reinforcement at congested zone also can be reduced, then it will result the design and detailing process become much easier. Okay, so this is the congestion of steel reinforcement at the intersections point. You can see that this is a lot of steels here. Okay, so this might be congested. Okay, so according to Eurocode 2 section 5.5, you can reach it. Permit the moment redistribution with the following requirements. So first is the resulting distribution remains in equilibrium with the load. The continuous beam are predominantly subject to fracture, and the ratio of adjacent span should be in range of 0.5 to 2, and there are other restrictions on the amount of moment redistribution in order to ensure the ductility of the beam, such as grade of reinforcing steel and area of tensile reinforcement, and hence the depth of the neutral axis. So class A reinforcement redistribute is less than 20%. Class B or C redistribution should be less or equal to 30%. So you can example here, okay, example here based on the result obtained from the example before this, redistribution of 20% of moment, okay, so means what? The original moment at the support is 231.21, so reduced by 20% is 0.8 times this value, so you will get 184.97, and this one at point C is 154.14 times 80% only, that is 123.31. Okay, so again you need to calculate manually for each reactions, okay, VA, VB1, VB2, VB3, and so on. Okay, so you need to read the same procedure as the moment distribution method. Then you plot the SFT envelope and also BMD envelope. So you can see the after 20% redistribution, the shear force and the bending moment diagram decrease. Okay, so thank you for this chapter. So see you for next chapter.